Today's activity is going to find for us a relationship, or I should say at least verify for us a relationship between some variables in the centripetal force equation. The lab is actually from your textbook, and it's on page 245 and 246 of your textbook. You don't really need those pages open while you're doing the activity if you listen carefully to what I'm about to say. But I'll just give you those pages so that you can refer back to it tonight, tomorrow night, as you're writing up this activity if you need to, okay? So page 245, 246, if you need to refer back to it. You may or may not need to refer back to it. What we're actually going to do today is to find or verify the relationship between the radius of an object's path going around in a circle and the speed of the object. In other words, we've got that equation, F is equal to mv squared over r. We want to verify this relationship r and v, the relationship between r and v. Now we have to identify before we begin what our variables are. Manipulated variable, our responding variable, and our control variables. Always remember, by the way, that there is going to be only one manipulated variable. There's going to only be one responding variable. And there's going to be, who knows how many control variables, a bunch of them. We're not going to have to list all of them because you might see 1,000 control variables. We want to list the ones that are important. What's the one manipulated variable? Well, if you take a look up here right now in my hand, you're going to see the basic apparatus. Okay, basic apparatus is going to involve holding a piece of PVC tubing like you see in my hand or like you see up on the board right now with a string going through it. On one end of the string is a rubber stopper right here. On the other end of the string is a 100-gram mass. We're going to swing this thing around. I'm not going to put the 100-gram mass on quite yet, the one that I'm actually swinging, but I'm going to swing this thing around. Okay, now this 100-gram mass is going to be what pulls back on the rubber stopper. You can see right now as I swing it around, I'm not holding the rubber stopper. I'm not pulling on the rubber stopper directly myself. Okay, it's the mass on the end of it, the 100-gram mass on the end of it, that's pulling down on it. Okay, that's what's providing the force for us here, the centripetal force acting on this rubber stopper. Now, what I want to do is change the radius of this path. Right now, you can see this rubber stopper is swinging around at a certain radius. Okay, you'd want to record what that radius is. And you'd want to measure the speed of this object as it goes around at that particular radius. Then you change the radius. You measure the speed at which it swings around now with that particular radius. Then you change the radius again. It doesn't matter really whether you're going up or down in radii. It doesn't really matter. What you want is a bunch of different radiuses, and you want to find the speed of the object that's required to get that radius. Does that make sense? So if we go back to here, who can tell me what the manipulated variable would be? Yep. Yeah, it'd be the radius, right? And what would be the responding variable there? We only had two variables that we were measuring, right? One was radius, one was, okay, so what's the responding variable going to be? Good. So your manipulated variable will be the radius, the responding variable will be the speed. Now your control variables, I'm not going to go through any of those because those are everything that remains the same. Usually in an activity, there's one or two control variables that are really important, and then there's about 1,000 other control variables that, it's important to keep them constant, but they're not as big of a deal. Okay, if you get those one or two really important control variables, and then a couple others, you're good. You don't need to list 50 of them. Okay, just list the important ones, basically. Okay? So back to the apparatus again for a second. You can see right here that we've got the rubber stopper on the end of it. We're swinging it around. We've got a 100-gram mass that's attached to the other end of the string, and that's pulling this rubber stopper back. When you swing this rubber stopper around, it naturally, the faster you swing it, the further it wants to go out. Okay? As I swing it faster and faster and faster, the rubber stopper wants to go further and further out. As I slow it down, okay, it wants to pull in like this. Does that make sense? What you want to do within each particular trial is keep the radius constant. Now, don't get confused with that. We're keeping the radius constant within a trial, but that doesn't mean it's a control variable because we're changing it from one trial to another. Okay, in trial 1, I want to keep this radius 10 centimeters or whatever. Okay, it doesn't have to be 10 centimeters, but okay, whatever its value is. Okay. Now that's going to be a little bit tricky because as you swing it and you change the speed a little bit, you're going to change the radius a little bit. So you're going to have somebody watching to make sure the radius stays at 10 centimeters or 20 centimeters or at whatever it's supposed to be. Does that make sense? You got to keep that radius constant okay, for that one particular trial. Then when you go on to the next trial, trial 2, maybe you change it to 20 centimeters. The next trial, trial 3, maybe you change it to 30 centimeters, and so on, and so on, and so on. Now, how do you know when you're looking at this that you're keeping it constant? Okay, you're swinging it around, and you may have to play with it for a little while to figure out how to get it at a constant rate, and at a constant radius. Because what's going to happen at first is you're going to start swinging it, and it's going to go all over the place. As you play with it a little bit, you should kind of master that and get it at a constant distance, a constant radius. Your partner's going to look at it and tell you whether you're keeping it at a constant radius or not. But the easiest way to do that, the easiest way for your partner to tell if it's at a constant radius or not, is to literally mark off your radiuses before you start. I've got Sharpie pens up here, and what I'm going to ask you to do is every 10 centimeters, 20 centimeters, 30 centimeters, 40 centimeters, 50 centimeters, I want you to mark off with a marker, with the Sharpie marker, that distance right on the string. Okay, that may already be done on your string. You should remeasure it and remark it just in case the group that did it before you in another class did it wrong. That make sense? Don't trust them. Maybe the apparatus got changed a little bit. Maybe they had to cut off a string because they couldn't get the rubber stopper off or whatever the case may be. So maybe it's not right. Double check it. If it is right, all right, good. If it's not right, then remark it and make sure that you know which one you're looking at. So if you've got a black mark right here at 10 centimeters, okay, then you're swinging it around. Make sure the black mark stays right at the PVC tubing. Make sure the black mark stays at that one point, doesn't move around. That's going to enable you to determine that the radius is staying the same for that one trial. Then again, for the next trial, you're going to speed it up a little bit and go to a radius of 20 centimeters. Again, it's going to take a little bit of practice. It's going to take you a little while to get this figured out in order to how to keep the radius the same within each trial, but you will figure it out, okay, given enough time. What do you got to record? Well, obviously you're recording your radius. Okay, that was our manipulated variable. Okay, and that's probably going to be 0.1 meters, 0.2 meters, and so on. Now we said the responding variable was the speed. We can't measure the speed directly. Okay, we have no way of looking at that rubber stopper and seeing how fast it's moving. So what we're going to do is measure the time of revolution. But I don't really want the time of revolution to be measured directly. I want the time of revolution to be calculated from the time for 20 revolutions. Anybody suggest why I want to do that? Why I want to find the time for 20 revolutions and not the time for one revolution? Yeah? Yeah. Your reaction time is too great. Okay, if you're timing it, time for one revolution is going to be less than 1 second. Your reaction time is going to be significant, and it may mess up the results there. If you time 20 revolutions, you've got a reaction time still of, half a second or whatever. But over a period of 20 revolutions, it's not that big of a deal. So record the time for 20 revolutions, whatever you get, 10 seconds or whatever. Do it again. Maybe you get 11 seconds for the next one. So on and so on and so on. Got that? From that, you're going to get the speed. Does anybody know how you're going to get the speed? From this? You guys know this. Well, let's get the average time first of all. So if we had, 10 centimeters, 10 and 11 seconds we had. My average time would be 10.5 seconds. The period would be 10.5 seconds divided by 20 revolutions, right? Because we want the time for one revolution, not the time for 20 revolutions. And then my speed would be equal to 2 pi r, 2 times pi times 0.1 meters over here, divided by the period. The period that I just found, 10.5 seconds divided by 20 revolutions. So now you've got one trial completed. Radius, time for 20 revolutions, time for 20 revolutions again, the average for 20 revolutions, then the period, which is the time that you got divided by 20, and then the speed, 2 pi r over t. Repeat that 5 times. These are your analysis questions, but for the most part, you would have already done your analysis questions. Question number 1 says, find the average of the 2 times. Well, you've already done that. Okay, so you don't need to go back and do that again. And I don't need to see down here in the analysis questions, I don't need to see that work done again. You should show a sample calculation every time you do a type of calculation. Okay, but I don't need to see it formally written as question number 1. Okay, you want to find the time for 1 revolution. That's the period. Okay, you've already done that. You want to find the speed. Okay, you've already done that. Again, show an example calculation of each one, but you don't have to answer these questions formally again. 4, identify the control, responding, and manipulated variables. You've already done that when you listed your variables. 5 and 6 are the ones that you haven't already done. 5 says identify the force that acted as a centripetal force and determine its value. Okay? If you listened carefully to what I said earlier, I gave you the answer to that. If you didn't listen carefully, or you did listen carefully and you just forget, or you kind of missed it, go back and watch the podcast, because literally the word-for-word answer to that question I gave you earlier. You can also think about it. Okay? There's nothing wrong with actually giving it some thought and coming up with the answer yourself as well. Number 6, here's the crux of this. Here's the really important part of it. Plot a graph of velocity versus radius. Or really, just noticed this actually. I copied this out from your textbook, but I just noticed a little problem with this. We shouldn't be plotting velocity versus radius. What should we be plotting? Speed versus radius, right? The velocity is changing. The speed isn't. So it should be speed versus radius. The speed, that's the first column that you're plotting. The radius, I should say, is the first column that you're plotting. The speed is the last column that you're plotting. The first column that you're plotting will always be on our x-axis, and the last column that you're plotting will always go on the y-axis. So the graph should look something like this. Speed versus radius. Now, I'm not going to actually plot the graph there because I don't want to show you the shape that you're going to see. Okay, I want you to do that. Plot that graph. And then question number 7, I haven't circled, although you haven't already done it. You will do number 7, but you're not going to do it right there with the analysis. That's essentially going to be your conclusion, right? That's your concluding sentence, right? Is what's the relationship between the speed and the radius? So we're not going to do number 7 formally. You're just going to do a conclusion, which is essentially going to answer number 7 for us. What is your conclusion? Well, what's your relationship between speed and radius? How are you going to determine that relationship between speed and radius? Look at your graph. Okay, you get a graph that looks like this, then the speed is directly related to the radius. If you get one that looks like this, it's directly related to the radius, but to a negative value. So in other words, as r goes up, v goes down. Does that make sense? If it looks like this, what's the relationship there? It's an exponential relationship, right? As r goes up, v goes up, but v goes up faster than r. Make sense? And so on and so on and so on. If you have any questions interpreting those graphs, and we're going to have lots of time to write this up, you can feel free to come and ask me some questions on that. I'm not going to give you the answers, but I will help you out with the graphical analysis. So your conclusion is, what's the relationship? Write down what the relationship is, and that's going to come from your graph. The second part of the conclusion is, how do you know? Well, how do you know? It's always going to come from your graph. You're going to say, well, it's a linear relationship. We know this because the graph is a straight line. It's an exponential relationship because the graph is a curved line upwards, or whatever the case may be. Finally, your sources of error. And you guys know with your sources of error that you need to list probably 3 good sources of error, but you also need to list ways to improve those sources of error. So if there was an issue with your time management, if there was an issue with the apparatus, if there was an issue with the procedure, whatever the issue was, okay, try to identify a way to make it better. Try to make this better for the next group that does this. All right? What do you got to hand in? Well, we need a problem. We need variables. Basically, the things that we've gone through here. We need your data. We need your analysis. We need your conclusion. Your analysis, by the way, includes those 2 questions. Sorry, includes your data includes the basic table That was your table of R and then time for 20 revolutions. Your analysis includes another table, which includes the period and the speed, but your analysis also includes the graph, and your analysis also includes those two questions. Your conclusion is those two things that we just talked about. First of all, what is the relationship? And second of all, how do you know? And then, of course, your sources of error are list 2 or 3 good things, good problems, good, that doesn't sound right? Good problems. Well, you can't have a good problem, I guess. 2 or 3 legitimate issues with this activity, whether it's your procedure, your materials, with your time management, or with the way you did it, or whatever, and then ways to improve that, right? Now, just a word of caution before you begin this activity. Okay, number 1, remember that as you swing this around, you're swinging the rubber stopper around, not the 100-gram mass on the end of it. Okay, the 100-gram mass is going to be hanging down. The rubber stopper is what's going to be swinging around. You could do it the other way around, but if something flies off, we would rather it be the rubber stopper than a 100-gram mass. The rubber stopper has less inertia than the 100-gram mass because it's lighter, and it's also a little bit squishier, so if it does happen to hit somebody, it's not going to hurt quite as much. Okay, having said that, we want to avoid hitting anybody with anything, including a rubber stopper. So what we've done is booked the biology lab across the hallway. We'll get some groups working in here, some groups working in the biology lab across the hallway, and we'll get 1 or 2 groups just going in the hallway, literally right outside the classroom. We want to be spread out. Everybody's going to be swinging these things around. We don't want to be hitting each other in the face or in the head or any parts of our bodies with anything, including the rubber stoppers. If we do have an accident, we'd rather it be the rubber stopper, but hopefully we don't have to even have that. Make sure the rubber stopper is the thing that's swinging around, not the 100-gram mass. Make sense? You can be in groups of, we'll go in groups of 3 here. Okay, go in groups of 3. 1 person will obviously be swinging this around, okay? And 1 person is going to probably become, of the 3 of you, you're going to find 1 person that's probably better at it than the others. So, okay, that person probably should stick with that role throughout the entire activity. 1 person will be responsible for timing the time for 20 revolutions and for making sure that the radius stays constant. The 3rd person, I would suggest the 3rd person does it as well, measures the time as well. Okay, so maybe you got 2 people measuring the time at the same time. Does that make sense? Does that make sense? Then you can do that for T1 and T2. Then you don't have to repeat the experiment, right? Okay? We're good there? All right, you're going to come up here, guys, and you're going to see each of these rubber stoppers already attached to the string. Okay, they're already threaded through the PVC tubing here, and you should find that the string is already wrapped around the PVC tubing. Okay, this is the way you're going to get them. It looks like this when you get it. When you bring it back to me, I want you to bring it back to me like this as well, and then just put it back in the bag exactly the way you got it. You're also going to see on this bench up here is the 100-gram mass. Okay, the value of that mass, if you look back here in your data, the value of that mass is important. I should have actually written that down right here. That's important. Right now, you may not see why that's important, but when you go to do one of those 2 analysis questions that you have to do, you'll see why it's important. Okay, so the mass should be 100 grams. We've played with this, gone a little bit lower, gone a little bit higher mass, and 100 grams is the mass that we find tends to work the best. So don't change that. Okay, technically, it doesn't matter what mass you use as long as you have it written down. We just find that 100 grams works the best, so let's stick with that. Okay, any questions on this? All right, let's get at it.